Hello everyone, I'm Melanie from Airbnb, and I'm here to talk about how we develop Kubernetes services at Airbnb scale. So first of all, raise your hand if you know what Kubernetes is. Hopefully almost everyone in the room. So yeah, it's an open source system for automating the deployment, scaling, and management of containerized applications. So I am a software engineer at Airbnb working on our service orchestration team. It's my job at our company to make sure the rest of our engineers are productive. And I think to go back into history helps illustrate how we got where we are today. So first of all, we decided, why microservices? So 10 years ago when Airbnb started, we had a monolithic architecture, and that worked for a while. But as you'll see from this graph, as our lines of code in the monolith grew to a very, very large number, it became hard to scale. Similarly, as we grew to engineering team to over 1,000 engineers, it became very hard to scale contributions to this one code base. And so you can think of introducing microservices as taking this continuous delivery cycle and scaling it. So each of these loops is basically another continuous delivery cycle and another service. So at Airbnb, I can't fit all of our services on one slide, but it's hundreds of services just like this. And this kind of illustrates the point. So this is a graph going back several years for all of our deploys per week. And this is all apps and all environments. So I think this slide illustrates two really good points. One, we have way more apps or way more services. And two, we have many more environments. So we started out just deploying to production, and now we deploy to a suite of pre-production tiers. So like canary, staging, load testing, development, and a few other testing tiers. So our developers are much more confident when the changes do go out to production. And I'm actually more excited by this graph, which is our monolith deploys per week actually leveling off. And so this really shows that we were able to move a lot of functionality out of our monolith and move it into these separate services, and developers just iterate and work on their own services without worrying about all the other services. And we're a big fan of deploying a lot. So we have 125,000 production deploys per year. And so we move very, very quickly and make lots of changes over time. So that was our first decision, which was microservices. But as we spent the last few years working with microservices, we had a few challenges. So going back a decade, we didn't have any configuration management. And a few years ago, we configured our microservices with Chef. And then very recently, we switched over to Kubernetes. And Kubernetes has a few more features than Chef that we like to take advantage of. So I'm going to break down what these advantages of Kubernetes are. So the language itself is declarative. It has efficient scheduling and an extensible API. So declarative means it's self-healing. You declare how many replicas you want. If one of the replicas has an issue, or if one of the pods has an issue, then Kubernetes will spin up another pod for you. Efficient scheduling for us has lots of cost-saving implications because we can schedule multiple services on one node or one minion in our cluster rather than having one node per service. And then the extensible API for us is very encouraging because we needed something that we could kind of extend and customize to our own needs. We didn't want some solution that made too many assumptions. We want something that we could kind of use ourselves. And Kubernetes under the hood uses containerization and Docker. And Docker has three neat features: portability, immutability, and reproducibility. So for us internally, we call this repeatable builds. This means that any time if you deploy a certain snapshot or roll back to a snapshot, the logic is the same. It cannot change. And so this prevents an issue. For example, before containers, you could just take an EC2 instance that was running your code, you could SSH into it and change something, and it would actually be changed for as long as that node was up. And so we had actually quite a few interesting incidents where we depended on people SSHing into a box, or we forgot someone to change something. And so using containers prevents this kind of incident. And then YAML is the file format. So some people probably are sick of looking at YAML files at this point. But for us, using YAML was actually very encouraging because the format, most humans understand it right away. And actually, a lot of our developer tooling services and systems, it's very easy for them to use YAML as well. And that kind of is a very brief summary of our history. I'd like to spend most of the talk talking about where we are today, the challenges and the solutions that we've faced. So today, 50% of our services are running in Kubernetes. We have hundreds of services. So right now we have about 250 to 300 critical services running in production. So actually, if you navigate to Airbnb.com today, the entire flow you take from looking at a listing and booking the listing and paying for the listing, all of those actions take place in Kubernetes, as well as several of our critical machine learning jobs and several other jobs that we have are also in Kubernetes. So we managed to migrate a lot to Kubernetes, but we had quite a few challenges. And I'm going to talk about those today. So complex configuration, complex tooling, integrating with your current infrastructure, making it work for you. Kubernetes itself has some open issues that are sometimes concerning, and you have to work around them. And scaling your Kubernetes cluster is also a big challenge. And more. And what I want everyone to know is that these are all solvable problems. I can't actually talk about all of these today, but we have solved and addressed all these problems, and I will talk about some of the solutions we came up with. And the solutions is kind of an outline of what we're going to talk about. So how do we abstract away this configuration, make it more simple, make it really easy to spin up new services, version and refactor it, and then have like an opinionated tooling system that makes it easier for developers to focus on writing and shipping code. And then finally, how can we catch and prevent issues at CI time and at CD time, rather than at apply time, when it's almost too late to catch issues. So I'm going to start with the first one, which is abstracting away configuration. So this is kind of what it looks like for a developer to work with Kubernetes. You have your Kubernetes cluster, and actually, as you saw right before this talk, you type kubectl apply-f quite a lot, right? You just keep applying files to make your final state. And so you actually have this grid of environments or namespaces and resources, and you have to sort of apply all of them to the cluster. And what we found is it's a lot of boilerplate, and it's very repetitive by environment. So we have quite a few environments, and they're similar to each other in a lot of ways. So how do we generate the different namespaces for developers? So reducing Kubernetes boilerplate. For us, we wanted to prefer templating over file inheritance, so having templated files rather than like a file hierarchy. We wanted the input to be templated YAML files, but we also want to support Kubernetes files if that's what our developers prefer. And two other considerations that maybe other companies don't have to deal with, but for us is actually very intimidating, right? Having to migrate hundreds of services to Kubernetes and having to retrain, at this point, over 1,000 engineers on Kubernetes. These are very challenging, so how do we make it easier for people to adopt this new technology? So this is on the right, the Kubernetes config files, and then on the left is our internal abstraction over Kubernetes. So we really distilled it down into a few ideas. Some of these map pretty directly onto Kubernetes concepts. The biggest innovation for us is sort of having a single project file, and that's kind of where we define all these parameters, and we're going to generate the Kubernetes files, or compile down to Kubernetes files. And so internally we call this kubegen for Kubernetes generate. So the way kubegen works is basically this project file, you'll see it on the right, sets parameters per environment. So the kubegen project file has like a version, so it's versioned like Kubernetes is versioned, and then it has a project name. For this talk, I'm going to talk about a test service called Bonk. It doesn't mean anything, it's just kind of a fun name. So I'm going to talk about the Bonk service as an example. So the Bonk service has a production environment and a staging environment, and you'll notice that production has 10 replicas and staging has 1 replica. Then in all of our other files, we can just reference these parameters rather than explicitly saying 10 replicas or 1 replica or auto-scaling or whatever. So in this case, the workload, the deployment workload file references .env.params.replicas. And when we actually run our generate command, it will generate all of the Kubernetes files by namespace. So in this case, when we run generate on Bonk, we have Bonk Canary, Bonk development, Bonk production, all of the different namespaces. And if you open each of these are the Kubernetes files. So this is what's generated. We generate quite a few things, so the admin role binding file, the config map, the service, the deployment, and we do it for all the environments. So with just a few files, I've actually generated probably 40 to 50 files for this service. So it really reduces the overhead for our developers. And standardizing on the namespace is actually really important here. So all of our namespaces are based on the name, which is bonk, and the environment, which is those lists of environments. One other thing we created is this idea of components. So when you have a bonk service or a foo service, any other kind of service, you'll notice that they have a lot of the same configuration. So there's like the service-specific configuration, but then they probably need like a logging sidecar container, or they need metrics. Maybe they need service discovery, like a service mesh, like Envoy. So all these components are things that all of our services need. So we have another way of abstracting that as well. So one example is Nginx. So we basically abstract away this common configuration into a component, and at generate time, we just sort of merge the component YAML into the project YAML to create the final project. So it's kind of like another generate step. The components can set default parameters, so basically developers can overwrite or extend things, or it'll just use the default. Similar to Kubernetes, where there's a lot of default variables as well. Cool, so that was an internal solution, but there's actually several open source solutions out there. So the three that I'll just list is Helm, Customize, and Capitan, and you can use the one that best works for you. So Helm is combined also with package management. Customize basically uses file inheritance, and Capitan uses templating. So our solution is some mix between these three. And our solution we came up with like several years ago, so these have been pretty recent developments. Oh. So the takeaways for generating Kubernetes configuration is that you should find ways to reduce Kubernetes boilerplate and standardize on environments and namespaces. So one idea we came up with after thinking about generating Kubernetes configuration is why not also generate service configuration? So we landed on this idea where if we could store everything about a service in one place in Git, and we could manage it with one process, then we sort of unlock all of these possibilities. So basically, configuration living in one place, we have our bonk service. So for all the configuration to live in one place in Git, for us that means it lives in something we call _infra. So you have your bonk repo in GitHub, and in _infra is where we store all of our configuration. So this includes Kubernetes configuration, which is _infra/kube, but it also includes CI, documentation, AWS.YAML, deployboard.YAML. These are some internal configuration that we also sort of model in a Kubernetes-like way. And you can basically edit both the code and configuration in one pull request, and it's easy to add new configuration. And then I'll get later into this talk that you can actually use CI and CD with all of this configuration as well. So here's just a big list of configuration we support. I'll go over more examples in a bit and kind of how we work with them. But basically, almost any configuration you can think of can actually be modeled in code, either as YAML file or markdown in the case of documentation. And so that's really powerful. So basically, this bonk service that I used as an example for this talk, it basically took me about 30 seconds to make in one command. And it's a collection of basically generators. So we have different config generators that will run. So docs, CI, and then we'll also run framework-specific generators. So in this case, bonk is a Rails service, and so I run the Rails generator. But we also support our drop wizard and Java services. So one thing that I think is really powerful here is that when we generate this configuration for our service developers, we're actually making decisions about what the default configuration should be. And we kind of have to encode our best practices in order to do that. So for example, we want all of our services to have all these environments, and we want them to have documentation and auto-scaling, and so our generators will use all of these options by default. We also wanted to support running generators individually, so if you decide later that you need something, you can run the individual generator, or you can run all of them as we do at project creation time. And we wanted to have a support for review, update, and commit. So basically, developers can decide which changes to take in or not take in. So it's kind of similar to a git diff. So the takeaways for this section is that everything about a service should be in one place in Git, and we want to make the best practice the default by generating configuration. One other thing I want to touch up on is once we store this configuration in Git, we can actually version it. So why do you want to version your Kubernetes configuration? Well, actually, Kubernetes itself is versioned, and so it made sense for us to also version our abstraction over it. We basically, whenever we add support for something new, or we want to change something like our default deployment strategy, or we want to drop support for something or make any breaking changes, and even when we realize that we've made a mistake in one of our earlier versions of our configuration, we know which versions have the regression and which versions don't have the regression. And finally, we wanted to sort of support a release cycle and cadence. So a lot of open source software actually has this idea of like minimally supported versions and like a stable version, latest version. So we kind of wanted to support this full release cycle for our own configuration management. So here is Bonk's project file. And it basically has a version field. And in this case, Bonk is on version 29.14. We publish binaries for each version, and then we have channels point to binaries. So we have a stable channel. For example, maybe Bonk is unstable, so Bonk is pointing to 29.14. And finally, all of the commands that our developers run will run the appropriate binary for the version that they have in their project file. So that's for the Kubernetes configuration, but actually one other thing we version as well is our generated configuration. So when I ran that command to create the Bonk service, if I run it today and I run it maybe 2 months from now, what I generate will probably be different because we work on the generator as well over time. So best practices change, and we find bugs in our generators as well. So there's many reasons why our generator would generate different things. And so we might want to know, for example, all of the services that were created with a bad generator version, or all the services that we want to sort of upgrade to a new format. So in this case, generator at SHA-2 has a bug, so we know that all the services created with generator at SHA-2 need to be fixed. And this is just kind of what it looks like. It's just a little comment at the top. So once we version our configuration, we can actually refactor them at scale. So why do we want to refactor configuration for service developers? So basically, our best practices change. The industry best practices change quite rapidly, and we want to make sure that all of our services are up to date with the best practices. And we want to make sure that when services are on an old version, that they're migrated to the new version. And even more important, let's say there's a high critical security vulnerability that we find out about today. We want to make sure that all of our services are patched with the fix as soon as possible. And we also want to just reduce toil and make it easy for developers. So if we can automate migration or refactor, then we'll automate it for them. So there's many reasons why we want to run refactor. And finally, I think it's fairly easy if you have 1 or 2 services to just manually go and change them. But as you get to the point where you have hundreds of services, you really need to figure out some way to automatically refactor services. So that's why we refactor configuration, but how do we do it? We basically have a collection of scripts. It's kind of modular, like Unix style. And we want them to cover the whole life cycle of a refactor. So in this case, we have scripts that retrieve all of our repos, and they can close PRs or list PRs, update the PRs, give you the status of the whole refactor. So we want to cover the whole life cycle. And this is actually kind of what the lifecycle looks like. So when you run a refactor across all these services, for each service, you kind of need to clone the repo, find the project in the repo, run the refactor job, and create the pull requests, tag owners, the people who own the service, on the PR, and then finally create the PR. And once we create the PR, some of our service developers are a little bit slow to respond, so we sometimes have to remind them about this pull request we created. So we have a way of basically commenting on the PR automatically to figure out, hey, have you taken a look at it yet? We're going to merge it in 5 days, so let us know. So basically, we give owners a chance to modify and edit the PR on their own. And if they don't do it, we actually generally have some kind of schedule. So for example, for a critical security fix, we will actually have some kind of policy. Maybe it's 1 day, maybe it's 7 days, but the PR will be merged at some time. And the way we do this is we kind of have a refactorator. That's kind of the fun name, Refactorator. What basically runs a refactor for all of our services, given a refactor job. So the refactor job, all it needs to do is modify something in _infra. So for example, if we want to upgrade all of our services to our latest stable version, that's one refactor job. Another refactor job updates all of our services' Docker files to pick up a security fix. One common task we have is bumping the stable version. So we actually use a Kubernetes cron job to do this. So basically, the cron job calls Refactorator with one of our scripts, and it runs the refactor job to create PRs. Another cron job handles commenting and updating and merging the PRs. So I think what I want you to take away from this is that configuration should be versioned and refactored automatically. And actually, one more point about that is, I think for versioning, it's very important to have that contract. So with Docker, we have immutability and reproducibility, basically by having the Docker image always be the same from that tag in your container registry. We want the same thing with the configuration itself. So by versioning the configuration, we have a contract that at that version, our tools will always interpret that configuration the same way. So it's very important from a reproducibility standpoint to version your configuration. So I talked about configuration, and I actually kind of want to switch gears to another topic, which is the tooling itself that you use to interact with your Kubernetes workloads. And for us, we actually have an opinionated kubectl, or the KTool. So the problem here, I talked about the configuration, is repetitive, it's a lot of boilerplate. But actually, if you look at the kubectl apply commands or the kubectl log commands, any of these other kubectl commands, these are also a very verbose and repetitive by namespace. So what we wanted to do is introduce duct tape, something to kind of stick things together for our developers, that actually calls kubectl commands on their behalf. And so yeah, this is the KTool. Not actually. So basically, the way the KTool works is it makes some opinions about how our service developers develop. So for example, we have the bonk service. If you CD into the bonk service, our tool knows that you're working with the bonk service. So for example, the way it works is you pass in environment variables. So if you CD into bonk and then run kstatus and vehicle staging, it knows what to run. So in this case, it runs kubectl get pods -- namespace equals bonk - staging. And so in this case, having standardized namespaces is very powerful because the KTool can assume that by being in the bonk service and providing the staging environment, that all of your commands are working in the namespace bonk staging. So the KTool has actually quite a few other functionalities. One of the things we wanted to improve was for developers, when they're iterating on their changes, how can we automate this stuff for them as well? So kgenerate actually will take our internal abstraction and generate it into Kubernetes files. And kbuild will actually perform your project build. So for our Java projects, it's a Gradle build. It will run a Docker build, and then it'll actually push to our container registry with tags. And so in this case, it pushes to ECR, which is our Amazon container registry. And then kdeploy actually will kind of create the namespace, apply or replace the files, and then check the deployment status. And what we want to end with is basically return an atomic success or failure for your deploy. And if you're much more lazy, like I am lazy, I will actually just have one command called kall that runs all of these for me. So when I'm developing, it's just kall, kall, kall. Finally, one thing we wanted to add is a debugging improvements for the KTool. So one thing I wanted to do is, if you have, let's see, how do I want to say this? Basically, for us, we have pods with many containers in them. We have the idea of a main container, which runs your server or your service, and we have a lot of what we call sidecar containers that run things like logging and metrics, and then service mesh and stuff like that. And so when you, in Kubernetes, when you run kubectl, you always have to provide a container name and a pod name in order to get the information you want. So we provided a command like kssh env = staging, and it knows that we want any pod, just get the main container that's running your service. And then like for another command, klogs env = staging container = bonk, you can also specify which pod and which container you want. One other thing to point out here is obviously kubectl does not have an SSH command as far as I know. It's kubectl exec bash, but a lot of our developers asked for how do I SSH using Kubernetes. After answering this question 10 times, I got really bored, so I said, okay, here you go, here's an SSH command. And so it kind of does what the developers expect under the hood. And finally, one other thing it does is it has a kdiagnose command, which is an even more way of trying to tell a developer what's wrong with their service. So together we have these commands that basically, under the hood, they're just running kubectl commands, and they'll actually print what they're running. So we don't want to hide from developers all of these commands that are happening. We just want to automate them, automate these workflows for the developers. And kubectl diagnose is actually a plugin I created, and I'm going to talk a little bit about that. So in Kubernetes, there's this concept of plugins. Actually, who here has heard of a kubectl plugin before? Okay, not that many people know about it. Some people do. But basically, this is a Kubernetes kubectl concept of basically creating your own custom kubectl commands. So you can actually create any kubectl command you want. And then the only thing you need, really, is an executable file in your path that starts with kubectl dash. So you can actually open up a laptop right now and then locally on your laptop create a plugin just by creating a file like that. So for demonstrating this plugin, I take my bonk service and it had like a bundle exec command, and I replaced it with a command that's doesn't mean anything. So I know that this service, when it tries kubectl applying the service file, it will end up in crash loop back off. So what do you do when your pod is in crash loop back off? For me, there's a few things I tend to check. I tend to check what are the containers and what is their state. Are they in unready or ready? And are there any pod events, any events to the cluster for my pod that may have affected my service? And then what are the logs for all of my unready containers? So these are the three things that developers, or at least me, manually look for when I have a service in crash loop backoff. But actually, my kubectl diagnose binary will just run all of these commands for you. And then at the end, it will tell you, basically it says something like, heyo, executable file not found in path. So it'll tell me the mistake I just made. So by automating this for our developers, we just took something that was a pretty painful debugging experience, and we'll try to surface all of the things we think might be wrong with your service. And of course, if there's nothing wrong with your service, it will say, hey, your service is fine. Don't worry about it. So we had this binary. So I wrote my kubectl diagnose binary, but how do I actually distribute it onto people's laptops? So basically, there's a case here for a package manager. You basically want to find a way to find, install, and manage kubectl plugins. And we want a way to package and distribute plugins on multiple platforms, Mac OS X, Linux, etc. And finally, you want a way to share your plugins with others. If someone has already created a kubectl diagnose plugin, I really do not want to have to re-implement it. I'd rather just use theirs and call it a day. Actually, I was looking around and I found an open source project from Google called Crew that does this problem. So Crew was unofficial. I think it's actually official now. And it's actually a pun on brew. So for those of you who use brew for Mac, Crew is like Kubernetes brew. And it itself is a plugin, which I think is really neat. So it's kind of like plugins all the way down. So the takeaways for this section is that I think you should create an opinionated kubectl wrapper. It's really easy to create like a makefile or a bash script, even on your own machine, just to automate some of your workflows. And then finally, you can use kubectl plugins to just make kubectl commands for like your custom needs. And then I would really encourage you to look at the plugins that other people are writing and see if those actually help you develop, and then use those plugins. And then give back to the ecosystem by writing your own plugins. Okay, so now that we've built our KTool, there's actually quite a few neat things we can do in CI and CD. So I'm going to dive into that. So this is what CI looks like for one of our services. It runs all these different jobs. So one that runs is validations, but it also runs build and build docs. What you need to know about our CI is it actually runs all of the steps in a CICD Docker file. So we actually use like a Docker file to build our project Docker file. And it runs K commands. So we actually also distribute our KTool to all of our worker machines, and so they also know how to run kgenerate, kbuild, etc. So that's our CI process really briefly. I think one thing that's really interesting is our deploy process, so I'm going to spend a little bit more time on that. So earlier I talked about all of your configuration stored in one place in Git and applied with one process. This is what that process is. It's basically your normal code editing flow. You write code on your service, you create a PR and merge it to master, and then you deploy all of your code. The only thing that's different here is that we're also doing this with our configuration. So it's the same workflow that every developer is familiar with. Actually, it's quite challenging to make this work, so I'll talk a little bit about it. So we have on our left our Kubernetes configuration, and in the middle is all of our custom configuration I talked about. So we have AWS configuration, project ownership, storage, alerts, documentation, service discovery, dashboards, secrets, API gateway. So all of these different configurations, like how do we apply them to our cluster? I'll first talk about the Kubernetes configuration, because it's actually, I've been saying kubectl apply, but that's not exactly what we do. It's a bit more complicated than that. So first we do try kubectl apply. There's actually some documented cases in Kubernetes where apply might fail, but replace without force works. So as a backup option, if apply fails, we'll do replace without force. And then we always restart the pods on deploy to pick up changes. So this is one opinion we had, which is some configuration is not applied until your pods restart and are replaced with new pods. And so we wanted to make sure that all of your configuration changes that you made when you deployed them was immediately reflected. So by basically always cycling our hardware on the deploy, we can immediately know whether it works or did not work. And then finally, we want to return an atomic success code. So we want to be able to tell our developers, your deploy failed or it succeeded. And this is a little bit hard because in Kubernetes, it's actually sometimes valid for your service to be in crash loop backoff and eventually not be in crash loop backoff. But we try to have an opinion that your services should never be in crash loop backoff. So they should start out by not crashing. And one question I get asked is, okay, so you always restart pods on deploy. Actually, how do you do this? So one thing we add to our pod spec is basically a date label. So the date is always changing. And this is actually enough to convince Kubernetes to relaunch all your pods. So that's like one neat way to do it. And then how do we apply the custom configuration? So I talked about Kubernetes configuration. Maybe you're actually already using a way to apply Kubernetes configuration, but for the custom configuration, it's a bit more challenging. There's something in Kubernetes called custom controllers. So Kubernetes itself is actually implemented from controllers, and this is how Kubernetes is extensible and easy to extend for your own use case, is because it's used with controllers, adding a new custom controller, it knows how to interpret that as well. So how do you write a custom controller? Basically, you have an aws.yaml file or a project.yaml file, any of your custom configuration. You need a way to apply it to the cluster. And there's 3 different things you need. So there's something called a custom resource definition, or CRD, in Kubernetes. So you create a custom resource definition for aws.yaml, and then you create a controller. For us, we actually create a generic controller. So all of our CRDs call the same generic controller. And the generic controller calls a webhook, and that is what actually updates your data store. So finally, you have a webhook that updates your custom resource. So for aws.yaml, the way we actually apply these changes to our Amazon account is with an aws.lambda. So our security engineers built this custom lambda that basically takes an aws.yaml, reads it, parses it, and then knows what changes to make to our Amazon account. And the most common change we have generally is IAM changes, like adding an IAM role to your service, or changing its permissions, security policy, stuff like that. So the takeaways here is that the code and configuration should be deployed with the same process. So they're all applied with kubectl apply. And you can use custom resources and custom controllers to integrate Kubernetes with your own infrastructure. So that's kind of how you use kubectl apply on custom configuration. Validation. So this one's actually really interesting. Once you store everything in one place in Git, you can actually enforce best practices. And you can do this at CI time or build time. And you can actually do this at deploy time as well. So how do we validate configuration at build time? This is kind of hard to read, but basically we have a project.yaml. This is where people store their ownership information. So in this case, for the bonk service, it's a tutorial project. It needs to have a team assigned to it. So one of our validation checks is that each project always has a team assigned to it. In this case, it's assigned to my team, which is service orchestration. It actually includes our whole org, so you can kind of see my organization structure. And in this case, it completed successfully. If my project.yaml file did not have teams, if it was empty, my validation would fail. And that CI check you saw a few slides ago would be red instead of green. So we enforce to our developers that they must have ownership. For us, ownership is very important. If there's anything wrong with your service, we need a way to route the alerts to the owning team. We don't want to have our infrastructure team try to figure out on behalf, try to figure out who to contact if there's something wrong with their service. So how do we validate configuration at CI time? Basically, we have this global jobs repo, and this is where we store all of our jobs. So all of our jobs are running using Docker, and so they're kind of defined as bash scripts that can be run. And our job dispatcher, we use a vendor solution for CI called BuildKite. But you can build your own job dispatcher, or you can use another one. For us, we have logic that basically dispatches global jobs to every single project. So if you take our bonk service, the bonk owner can define their own project CI jobs, and the global job will always run the global jobs and the validation jobs in addition to whatever the bonk CI jobs that I configured were. So that's kind of how we ensure that we're always running the CI checks. So it's sort of a mandatory global CI check. What do we check for? There's actually quite a few things we check for. So invalid YAML, it's pretty common for someone to indent something incorrectly, or like, I don't know, stuff that you really don't want to be stuck on and like realize it was invalid YAML, so we'll like catch that for you. We actually know certain invalid combinations of Kubernetes configuration. So for example, you really don't want to have auto-scaling and define replicas. So we'll like catch things like that. We can catch bad configuration versions. So I talked about we have regressions in our own configuration. Kubernetes has regressions in their configuration. By versioning it, we know that there's certain versions that are bad, and so we can catch that at CI time. One fun fact is the namespace length in Kubernetes. So if your service is too long, with our environment, so if your service is really long and then we add development, then the namespace ends up exceeding the maximum DNS length, we'll also catch that. And two other things we check for is just a valid project name and the valid team owner. So that's CI time. And actually at deploy time, or CD time, we use another Kubernetes provided solution called admission controller. So Kubernetes has something called admission controller that intercepts requests to the Kubernetes API server prior to the object persisting to the data store. So this basically stops a deploy or an apply from actually happening. So this is quite a bit stricter than CI failing. This prevents your deploy from happening, makes your deploy fail. So we want to be careful about how we do this, but there's some things we want to ensure. So how we do this is basically metadata about your service are encoded as Kubernetes annotations at generate time, and the admission controller checks for required annotations. So some required annotations is like that you're using Git. So for us, you have to use source control. Another required annotation is project ownership. So we basically reject the update to any resources that is missing the required annotations, and we'll also reject updates that violate specified conditions. And I'll go over these conditions on the next slide. So yeah, I talked about project ownership, annotations, configuration stored in Git. We basically have the minimally supported version, so we don't want to support versions that are too old, and so we'll actually reject those. And we also test a few other things. Production images have to use our production ECR, so we actually separate development from production, because we don't want them to affect each other. We prevent deployment of some unsafe workloads, and we also prevent the deployment of development namespaces to our production clusters. So a lot of these actually is another benefit of standardizing on namespaces. When we standardize on namespaces, we know that this namespace is a development namespace, and that it has no business working with production, container registries, production clusters, etc. So for CI and CD, the takeaways here is that they should run the same commands that engineers run locally. I think what's important about this is that when a developer is using the KTool on their laptop, they become very familiar with it. And so that if there's a CI failure or a CD failure, they can see what the failure is, and they're also familiar with that failure. And they can also reproduce the failure on their laptop. And then finally, when there is a production incident or downtime and there's something wrong with their service, they very urgently have to figure out what's wrong with their service and fix it. Thankfully, it's also the same tool, so they're building familiarity with both their development tooling and their observability and production tooling at the same time. CI/CD should run in a repeatable environment so that it always is immutable, reproducible. So it should run in our case, it should run in a container. You could also run it in serverless. And finally, I think you should validate configuration as part of CI and CD. So if anything you can catch automatically, you should catch, and you should catch as early as possible. So CI is the earliest you can generally catch it, and CD is sort of the latest time you can catch it, so with the admission controller. Cool, so the 10 takeaways, I put them all on one slide for you, so you can take a picture of that, because I tend to move kind of fast. But the 10 takeaways are basically abstracting away the Kubernetes configuration and standardizing on the environments and namespaces, that sort of guiding principle that everything about a service should be in one place in Git. We want to make the best practices the default by generating configuration. We want configuration to be versioned and refactored automatically if possible. And I think it's very important to create an opinionated kubectl wrapper that automates common workflows and runs them as kubectl plugins. And finally, CICD should run the same commands that engineers run locally, and you can validate configuration as part of CICD, and that code and configuration is deployed the same way, and you can use custom resources and custom controllers to integrate with your infrastructure. Cool. So those are some of our solutions that we came up with over the last few years, but we actually have quite a few challenges looking into 2019. So these are the personal challenges that Airbnb is still facing. I won't list all of them, but it's here for your reference. If this seems like interesting work for you, Airbnb is hiring engineers in multiple offices, and we actually have a careers page, and you can DM me or @ me on Twitter as well. So I'm Melanie Cebula from Airbnb. Thank you for listening.